Okay, so welcome to the fifth workshop about the causal inference community. And this is a workshop held by the Swarma Club, which is the biggest and most influential causal community in China mainland. So in the fifth workshop, our topic would be the causal inference and the large language models. So which is a hot topic since the launch of the ChatGPT. So more and more people they are get interested in the large language model. So as a most influential causal community, so we want to know so how causal reasoning and the large language model can be a two-way road. So how could they help with each other? So that motivates us to launch the fifth workshop entitled the causal inference and the large language model. So I am Haoxuan Li from Peking University, now as a PhD candidate in majoring in the data science and the statistics. So I'm a co-organizer of this workshop, and we are so honored to invite the Amit Sharma to give us a talk. So let me introduce something first. Okay, so as I just said, so this workshop is held by the Swarma Club, and the Swarma Club. So we want to have the cross-sectional, so focus because we have very diverse audience, so focus on different regions, and meanwhile we want to give a systematic review of the complex science, and we want to provide some future direction and important scientific research problems to our audience. And each talk will hold between 2 hours, or it might be as long as 3 hours. So for each period of the workshop, we will hold 8 to 12 times. I just said that this is the fifth workshop about the causality held by Swarma Club. So let me briefly go over the first four causal workshop held by this community. So for the first workshop, we focus on the basic of the causal inference and the causal AI framework, and we apply the causal AI and the causal agent to a variety of the different regions, such as economic, psychology, medical science, healthcare, etc. And we focus on the two causal frameworks. So specifically is Julia Pearl's structure causal model and the Rubin's potential outcome framework. So we introduce each framework systematically from the most famous textbook. We invited different speakers to share their opinions within both the Rubin's potential outcome framework and the Pearl's structural causal models. And for the second one, so we focus on help the audience to have basic programming and to implement the causal algorithms in their own regions. So that motivates us to introduce the basic of the implementation of the causal AI or causal algorithms. And for the third period, the topic would be the causality plus X. So which means we want to apply the causal to different areas, such as a recommender system, as a NLP, as a computer vision, and we invite, the experts from the different specific regions to help us to know how to apply the causal knowledge to the different, sub area and to improve the out of distribution or the explainability of each region. Before the launch of the fourth period, so there's a very famous paper entitled Towards Causal Representation Learning. So this paper is written by the Yushuga Benjo and the Bernard Shukov. So they talk about the importance of the causal representation learning, including the IDA or the other, technique tools to help us to identify and to learn the causal representation. So we focus on how to both theoretically and empirically to learn the causal representation in the fourth period. And now we have attracted more than 2,000 professional audience in this causal community. And from these figures, we know that our audience is diverse and professional. So for the fifth period, so our we just now we focus on the causality and the large language model. So we divided by 4 parts. So the first part is we want to leverage the large language model for the causal discovery or the causal inference. And then we want to focus on the causal inspired large language models fine-tuning. So we want to leverage the causal knowledge to improve the reasoning ability or the trustworthiness of the large language model. And we also interested on the benchmarks of the intersection of the causality and the large language model. For the third part, we focus on the multimodality ability of the large language model. So we want to apply the causal ideas to the problems like the VQA problem, the causal prompt strategies, or to answer the vision questions as well. And at the fourth branch, we want to focus on the most recent advance to leveraging the causal representation learning or causal reinforcement learning or the causal data mining. For example, we have found some papers about using the causal ideas to improve the large language model on the recommender system or the information retrieval. So that is the whole picture of this period, this amazing workshop. And I'm Haoshan Li, which is a PhD candidate from the Peking University as a co-organizer of this workshop. And my co-organizer, including the Dr. Mengyue Yang from UCL and Dr. Guangyi Chen from Carnegie Mellon University and MBZUAI. So today we are very honored to invite Amit Sharma, who will give a talk on his one of the most important research. So I think that is a very early and very influential research focusing on the intersection of the causality and large language model. Okay, so let me briefly introduce our invited speaker. So Amit Sharma is a principal research scientist at the Microsoft India, so focusing on the causal inference and machine learning. So he received his bachelor degree from the IIT and received her PhD degree from the Cornell University, supervised by Professor Dan Costley. So during the 2015-2017, he worked with Jake Hoffman and Duncan Weiss as a postdoctoral research fellow at Microsoft Research New York. And his research is aimed to develop the trustworthy artificial intelligence system and to explore the application of the causal inference in recommender system, fairness, and explainability. So in the causal inference aspect, so Amit Sharma and Emery Kitchman, they write a book, entitled Causal Reasoning: Fundamentals and Machine Learning Applications. So I have read a book, which gives much insight about the causal reasoning, and he contribute one of the most important open source framework, which is a Python toolkit named DoWhy. So today we are very honored to invite him to talk about his very important early work focusing on the intersection of the causality and the large language model. So let's welcome Amit Sharma.
Thank you so much for the introduction. I think it was really good to see the community that you're building and the different kinds of causality topics that will be covered. Thanks a lot for inviting me. As Haksha mentioned, I am Amit Sharma and I work at Microsoft. I'll try to talk to you about not just this paper that we wrote last year, but also what we have learned subsequently and where does this answer to the question lie? Can LLMs do causal reasoning or not? Um, and I think our motivation last year when we did this paper was that there was just so much information about GPT-4 and GPT 3.5 doing all sorts of amazing tasks, right? And so the first thing we thought was, since we are causality researchers, can we also evaluate these large language models on causal tasks? And so that's what I'll present today. Also with some hindsight on what we know now that we did not know when we wrote this paper. And I mean, you all are aware causality is a really important problem because even in healthcare, it's not just enough to know what will happen to me in the next 2 years. I also want to know if I take an action, let's say if I exercise, what will be my health in the next 2 years, right? And this is not just in healthcare, these kinds of questions appear all across our society. It happens for business, of course, like marketing or figuring out how to send messages so that you have the most impact. But it also happens in government policy. For example, you might want to know whether a government regulation leads to a decrease in air pollution. So I think almost everyone would agree that causality is super important. Causal models are very useful. Yet, if you look around, causal models are not widely deployed. And this has been a very perplexing situation for many years, where a lot of us are working in causal research. There are so many amazing models and algorithms that have been built using causality. Yet, you won't see a lot of industry or a lot of governments deploying causal models. And I think the common refrain that we hear uh, from people is that causal modeling is not practical. By that, sometimes they mean that I don't know what assumptions I need to make. But more often, it's just that usually you need a graph or usually need a set of domain assumptions to even start causal analysis. And getting that graph itself seems to be a really hard task for people to start with. The reason I'm telling you this is because the single biggest observation we had when we tested LLMs for causal inference was that large language models are good at memorizing the entire world knowledge, which means they can generate graphs for almost any situation that you may need it for. And I think that was the biggest discovery for us, was that any field, you could take physics, you could take engineering, you could take biology, you could take social science. And we found that across all these different topics, uh, LLMs like GPT 3.5 and 4 are very good at determining pairwise causal relationship. And in subsequent work, we have found that you can also use that to then construct full graphs. So the biggest point was that LLMs may not be doing causal inference, and we'll come to that throughout the talk. They are not doing formal causal inference as we know it. But at the same time, they are kind of taking the role of the domain expert that before LLMs used to be overburdened, right? So before LLMs, the domain expert, we expected to give us the graph. And then we also expected the domain expert to somehow make the assumptions required for testing the robustness of a causal estimate, right? And so in some sense, causality was highly dependent on a domain expert. I think what LLMs are changing is that first, the domain expert's role might be now just to look at the graph generated by the LLM and verify it. So their time will be reduced. And second, we are also finding, as you see in this second point here, that LLMs are also good in many of the tasks that need human input. So for example, counterfactual inference from text, where again, there's not even a graph. I mean, if I just give you some text and I ask you what will happen if something in the text is changed, it's even hard to construct a graph because you need to know some domain knowledge or some world knowledge about what that text is saying. So even there, actual causality is a field. It was not used very widely, but I think now because of LLMs, even actual causality will start becoming much more productionized, much more algorithmized, so that we see more of such systems. And so the future that I'll talk about is not that LLMs will replace causal inference methods or causality models. That's not the case. In fact, I don't think they are doing causal reasoning the way we, for example, the way Yudia Pearl would say causal reasoning works, right? I don't think they're doing causal reasoning, but I think they're doing something special in capturing the world knowledge across all sort of different fields, so that one, they can actually give us causal graphs, and second, for most real world situations where the graph is not easy to get, they can also give us useful counterfactuals. How they do that is still a matter of question, but it's good to know that perhaps they're not doing the exact causal reasoning. I think they're doing something else, which also gives us the same results. Okay, so what I'll do is I'll first just go deeper into why causality was not applied so widely. What are the fundamental challenges in causal modeling? And then one by one, we'll see how large language models can potentially solve these challenges. At any point of time, if you have questions, feel free to stop me. Okay, so let's take a pause, right? So even before thinking about LLMs, let's just look at two fundamental challenges that causal inference has. Uh, the first is that you have to learn the causal relationships. Right? Even before starting, let's say, a causal representation learning task or a causal inference task or a root cause analysis task, typically it's important to have at least a few assumptions, right? So you want to know which variable causes other variables. And the most simplest question of them is, given two variables, does A cause B or B cause A? And people have shown that this is theoretically impossible to infer if you just have access to observed data under no parametric assumptions, right? Of course, if you make some assumptions, it becomes possible with methods like Lingam. But in general, this is completely open problem. And the second is you have to also represent the causal concepts. So if I just give you some text, which is usually the way real world data is present, uh, we need to somehow have methods that can extract causal relationships from this text. And even that was too hard. And as a result, we were not really engaging with a lot of sort of data heavy uh, machine learning. And so really predictive machine learning was often being used, but not causality. But it's also very hard, because if you just have observed data and you look at these two relationships, you might think that they are causal, right? There's a correlation from 2000 to 2010. So you might think that they are causal. But I think the only reason we know that this may be a spurious correlation is because we can also look at the names of the variables, right? So look at the x-axis, that is a computer science doctorates awarded in the US. If you look at the y-axis, that's total revenue generated by arcades, which are game parlors. You play video games there. And so now you can obviously say that, no, there has to be no correlation. Computer science PhDs play some games, but probably not so much to move the entire industry, right? So that was the first sort of fundamental insight that large language models give us, is that just like humans can reason about causation from variable names much more efficiently than looking at these plots, LLMs will also give us the same ability. And I'll show experiments of that. But also, we should remember that it's probably impossible if you just look at the data, right? So I think the revolution that we will now see is that more and more algorithms will be developed which combine the power and reliability of methods based on data with the domain knowledge that LLM gives us. Right? And so we'll see now these kinds of provably impossible results being broken, because now we don't just have access to the data, we'll also have access to the names of these variables. And full graph structure, of course, it's really hard. But I think there are now results that you can extend those kinds of pairwise results from LLMs to even go to full graphs. And so one thing that I want to note is that while LLMs and existing methods will combine, uh, before LLMs, there was still a very sort of sobering results of how we can use these graph discovery algorithms on real world data. In fact, they would work really well on synthetic data or existing benchmark data. But when people have tried to apply graph discovery algorithms to real world scenarios like healthcare or Arctic climate science, they found that the graph discovery algorithms were not as good. And so what we'll do is that we'll take exactly these data sets from healthcare and Arctic climate science, and see how well GPT-4 or GPT 3.5 can do on these tasks. We'll also look at some very basic causal questions, such as effect estimation, counterfactuals, attribution, and show how, if you have the correct graph, you would be able to now also answer these kinds of questions. I think the second problem that was a big problem for deploying causal research in practice was that we would not even think of you doing causal inference on text before LLMs, quite honestly, right? Because before LLMs, if I give you this kind of a healthcare report, this is a healthcare report of some person who's suffering from some disease. There have been a lot of NLP papers on predicting things like what variables are in this report, what is the disease this person is suffering from. But there were very few papers on analyzing causality here, which would say that what should the causal graph even contain based on this summary. Right? So of course there should be some variables which are mentioned in the report, but there should also be some variables which are not mentioned in the report, which might be assumptions like, oh, this person is already in a hospital, right? If they're going through some test, perhaps this is the kind of problem they might be suffering from, right? Not everything is mentioned in this small sample, but you need some world knowledge to know that, oh, if someone is suffering from this kind of disease, maybe this is the kind of body problem they might have, or this might be their relative other kinds of variables. And so what we find is that before LLMs, it was really hard to even think of causal inference on this kind of data. But as I'll show some experiments, there is some evidence now that causal researchers can even tackle text data, because now you can kind of use LLMs to construct some graphs for you, or use LLMs to even give you some structure on these kinds of data sets. All right, so that was the prelude. Now I'll jump right into the paper's results. We'll look at graph discovery first, and then counterfactual inference. Any questions so far?
I think no questions.
Okay. So as I mentioned, right, our motivation was that large language models were transformer-based generative language models. They've been trained on next token prediction. And we were seeing so many results last year, which were showing this process of emergence. Right? They were saying that as model scale is increasing, there's a lot of ability in language understanding, programming, creative writing, etc. So we asked a simple question, what about causality? So of course, we had no idea. So we thought, let's just do some basic tests. I remember the example from Yudia Pearl's book on rain, sprinkler, and wet grass. Maybe many of you are also familiar with this example. It's used very popularly to teach causal inference. So we thought, okay, let's just try this question. Let's see what ChatGPT gives us. So we first asked us to construct a causal graph between these three variables. And ChatGPT gives a long response. But if you look at the bolded answer, it's actually correct. So this is surprising, right? I mean, this is a model that has been just trained on web data, and somehow it's able to give you the right answer of a very technical concept, which is a causal graph. And it's also kind of giving you an explanation. So at first we were surprised, but then we thought, wait, this example is from Pearl's book. It is very popular. So maybe the LLM has just memorized it, right? That's possible. So then we tried a slightly different example. If you look at this prompt, it's almost the same, except that now we are saying that the wetness of the grass we are interested in is indoor, right? So we are doing that just so that rain would now not affect this grass, right? So now it's a very new situation. I don't think any book would mention this situation. And also, if you look at the text is now almost the same, except that indoor is mentioned once or twice. And now you would see that the graph that is presented is not exactly what it is, right? So now it's kind of saying that rain might influence when someone decides to turn on the indoor sprinkler, which might be true, but I think it's not exactly what we had asked, right? So this also gives you pause, and you think that, GPT-4 is not perfect, right? But the interesting part is that there is something here. It is not bad either. Right? And so what we want to know is first, how robust is this capability? Does it only work on examples it has seen, or it can actually generalize to new domains? And the second thing we also want to understand, at least partially, is how is it doing it? Right? This has been such a hard problem, even for people, even for domain experts. It's often a hard problem to construct causal graphs. So we also want to understand how exactly is GPT-4 able to do it. So we thought, let's just measure first, right? Even before making any hypotheses, uh, let's just do a very proper measurement of these language models' ability on causal discovery. And the way we'll do that is that we'll take existing benchmarks, which are very popular, and test the LLMs on pairwise discovery, where the question is, given a pair of variables, decide whether A causes B or B causes A. Second, we'll also take some less known data sets. And this is important because we want to test memorization. So we'll also take some data sets which are very unlikely to have been memorized by these language models, just because they were not available on the internet, or perhaps they were available after GPT-4 was released or after its training cutoff date. And we'll do the same analysis, right? So we'll try to see how accurate they are in inferring the full graph. So for the first study, we took a very popular benchmark, which is called the Tübingen benchmark. This has 104 variables spanning a range of fields. So as you can see in the image here, there is zoology, biology, engineering, physics, and so on. So it's a very diverse set that can check how well the LLM generalizes to different topics. And it's a very hard benchmark. I think even recently, so I think the best algorithm was getting about 83 or 84% accuracy. So the first question that comes with LLMs is the prompt, right? Because these are black box models, we have to think about what prompt we can provide. We tried two strategies. I think the first one was 2 prompts per pair, which is we'll ask the does A cause B question, and then secondly, we'll ask the B cause A question separately. But very quickly, we realized that actually a single prompt is much better, where we just ask one question, which is which causal effect is more likely. Option A is A to B, and option B would be B to A. I think since we have done this paper, a lot of better prompting strategies have appeared. But just for the sake of evaluation, it's good to have a simple prompt and then see how good LLMs can do. Okay, so let's look at the first example. This is an actual prompt from our data set where we wanted to ask about a organism called abalone. And the question asked is, what is the relationship between their length and age? So if you look at the first picture on the left, we get the right answer. Right? Now we just slightly change this question. This is also a question from the data set, where now instead of the age and length, it becomes age and diameter. And now you see that the LLM gives a wrong response. So at the end, it's saying that changing the diameter of an abalone will change its age. Now, we all know for no animal this would be true, right? So this is again to show that we get a similar signal across our study, that the first few experiments we try, we are impressed. But at the same time, when we try certain variations of that same experiment, the accuracy decreases. So again, I think the message I want to take home is that there is a lot of causal reasoning capability in large language models, but they are not robust. Right? So what it means is they're probably not doing formal reasoning. They're probably not doing the counterfactual or formal causal reasoning that we all are familiar with. But still, at the same time, I think they're able to get a lot of high accuracy, which means that we should really think of them as helpers or as assistants to any causal reasoning agent. So how are the results? As I alluded, their accuracy is very high, but let's start from the existing methods, right?
So the existing methods were getting about 83% accuracy. We first tried some 2-prompt templates, and we found that with the small models, accuracy is almost as good as random. They are not that useful at all. But with GPT 3.5 Turbo, we were able to almost match the accuracies that were available as the state of the art using data. And then finally, when we tried GPT-4, this was a one-shot experiment. We were not prompt tuning. In fact, we did not even have access to GPT-4 earlier. When we got access, we just tried the exact same prompt that we had with GPT 3.5. And we were surprised to see that it had a really huge gain. And so I think right now, the state of the art is about 97% on this data set. One thing I want to note is that the methods in prior work were covariance-based. They were data-based, whereas the methods from LLMs are knowledge-based, right? So they're doing two different things, which means that there's a lot of potential to now perhaps combine these two kinds of algorithms and get even better results. But just the fact that based on variables, you can get 97% accuracy is quite surprising, right? And it kind of opens up a new way of also engaging with causal inference data sets. But still, as I mentioned, right, sometimes you will find some interesting cases which will hint at reasoning. And at the same time, you'll find some cases which will hint at some completely wrong answer. So in this case, let me give you an example which will point at some kind of reasoning. So when we first asked the question between ozone concentration and radiation, we got an answer which was incorrect according to the benchmark, right? And the reason was because the GPT interpreted ozone concentration as that of the stratospheric ozone. But when we tell it that, no, we are actually asking about the ground level ozone, which was what the data set mentioned, then it actually is able to give the right answer. So there's still enormous amount of knowledge that this model has, and it is important to prompt it correctly, or at least clearly. Your question should be as clear as possible to increase accuracy. But I think a lot of you might be thinking still that it could just be memorization. I myself mentioned that Tubingen is so popular, hundreds of papers have been written about the Tubingen dataset. So maybe the LLM has just memorized it. So the second task that we looked at was something called neuropathic pain dataset. This is a very recent dataset, and it's not even available on the web, in the sense it's available on GitHub, but you have to write a Python script to actually get the graph from that dataset. So we thought maybe this is slightly harder for a language model to have been pre-trained on. Maybe it's pre-trained on the code of the dataset, but perhaps not the dataset itself. So we thought, let's try it on this dataset as well. It's also more interesting because if you look at the variables here, I cannot make out what they were. Like unless some of you are medical experts, you would not even perhaps able to know what these variables are meaning. And that was an interesting part, right? So we wanted to see if LLMs could also do well in very highly specialized domains. And what we find are similar results. The smaller models like Ada, Babbage completely cannot do this task. They're as good as random, 50% accuracy. GPT 3.5 reaches about 75%, but GPT-4 with the exact same prompt, no prompt tuning involved, reached 96%. This was shocking to us. The first data set, we could still assume that maybe it's possible, but the fact that these language models could also generalize to highly specialized domains was shocking, right? Now, of course, now 1 year has passed, so you can obviously think about these are really big models. They might have been trained on research papers about medicine as well. So maybe it's not that surprising today that LLMs can actually memorize information across so many different fields. But I think when we did the study, we were really shocked because we thought this would be a hard data set. Right? We thought this is such a hard data set, we will probably not get great results, but we did. And sometimes we also find that there are some relationships predicted by the large language model that are not in the current data set, but regardless, they are likely. So one relationship was between L5 radiculopathy. Oh, by the way, this data set I learned while doing this analysis is about pain. So the radiculopathy is a kind of pain that you get, and it's a symptom of some nerve being damaged. And the question was whether L5 radiculopathy can cause obesity or vice versa, right? So this data set says there's no relationship at all, but actually the LLM says that no, obesity can cause L5 radiculopathy. And when we looked at the literature, just a brief scan of the literature, I was able to find 2 papers which have been written which claim that obesity may be a risk factor for radiculopathy. So quite interesting results where in the future, we believe LLMs could also help domain experts create graphs and maybe also release benchmarks by testing it with LLMs before releasing it. Was there a question?
Yeah, hi, Amit. I found a question in the chat box.
Okay. Can you tell me the question? I can't see the chat box.
Oh, so our audience Ihan asked, is this suggesting that causality might be a phenomenon of language, a language level patterns or rules or laws? So he wants to know, is this suggesting that causality might be a phenomenon of language?
That's a great question. I think probably not. I don't think causality is only restricted to language, because even before language was invented, causality still existed in the sense that the sun would make the earth go round and you could create fire by breaking 2 stones. So even before language, I think these facts were causal facts that doing some action like touching 2 stones together will lead to fire, right? Having said that, I think in the modern world, much of our causal knowledge is actually domain knowledge, right? So for example, the fact which kind of pain is caused by obesity or not, and so on, is a very domain knowledge or a field specific information. And maybe there the question is saying something correct, that a lot of what we believe today as causal knowledge is really just book knowledge or bookish knowledge, right? That a lot of people before us have collected. And I think what I'm trying to say is that all of that knowledge is now possible to be extracted using large language models. So yeah, I think I don't believe that causality itself is a concept in language only. I think it also exists outside language. But at least for the most practical use cases that we apply causality today, we do expect to consult books. We do expect to consult information already present in natural language. And I think that's where LLMs are shining. Another way of thinking about this is that it's remarkable how much of human knowledge, or perhaps I would say the vast majority of human knowledge, has been encoded into text. And this is what LLMs are exploiting, that even this fact, which was discovered without natural language, the fact that if you strike 2 stones, you'll get fire, it was discovered without natural language, but right now it has been written down in natural language by multiple people on the web. And maybe that's the real answer here, that most of the useful knowledge today has already been written down. And that's why LLMs can get back that useful knowledge.
Yeah, and another question raised by the audience is, did you test out the prediction on the connection found in new results? So the audience said this could be easily done by asking yes or no question about a new published data or paper.
Yes, yeah. So we have done that. I won't have time to cover it in the talk today. But what we tried was we looked at scientific papers that were published after 2021 September, which was the training cutoff date for these models. And we also looked at books published after that time. And we tried to find causal relationships predicted or mentioned in those publications. And we tried these same exact LLMs on those questions as well. And we found similar results. I think the accuracy is always above 90% for these different kinds of tasks that we tried. We also tried, there was a causal graph released in ICLR by some researchers. That came in ICLR 2023, so very recent. And we thought, oh, this is interesting. Here's a new graph that was not even present in before, because this was now created by doctors. How about we try our LLM on this graph? And turns out we found that even for that graph, we got high 90% accuracy. So I think we've done multiple experiments now to make two conclusions. The first is that the power of LLMs to do causal discovery is not restricted to existing data sets. And it's not restricted to only medicine. I think it can cover all kinds of science knowledge. That's the first result. The second result is that even though you get high accuracy, don't be fooled, because it's very unreliable. You might be getting 90% accuracy on your task, but once you look at the errors, you'll find some very stupid errors, or you'll find errors which are completely nonsense. And so you just have to be careful. Like, even though you can get high accuracy, these models are still not reliable. And many of the errors that they're doing are clearly showing us that they are not causal reasoning systems. They are close, they are very close, but I think that there's also a lot of unreliable errors that they make. So we have to be careful when thinking of deploying them. The best use case I found them is like as an assistant to a human. So you use them as an assistant, you already get some output of a graph from them, but there should always be a person or an expert then looking at the graph and verifying it.
Amit, I have a question for you. Because if I
Sure.
understand correctly, so you say you have a data set whether the radiopathy causes obesity.
Right.
So that's the truth in your data set, right? And then you use a ChatGPT 3.4. They got the different results than what's the truth in the data set. Is that you discover?
Yes. Yeah.
Oh, that's I mean, so that just shows basically the ChatGPT is wrong, but I don't understand your say is also correct. Basically, the ChatGPT gets the wrong answers. But why you say is correct?
I think it's because medicine is complicated. So what happens is, if you have this L5 radiculopathy problem, you will be at a higher risk of obesity, right? So that is true. But let's suppose there's some other person who does not have L5 radiculopathy. They have obesity. So there have been recent papers in the medical literature which show that if you have obesity, then they have a higher chance over time to develop L5 radiculopathy. So this causal relationship goes both ways, but maybe it's more common to say the first one. I think the first one is a much more well-established relationship that doctors had created. But I think the other one is less common, but there have been scientific papers written claiming that relationship as well.
But one thing we'll have to keep in mind, all the AI model is population-based results.
Right.
They're not individual results. I don't think you can draw individual results based on either ChatGPT or based on the AI modeling. So what do you say that? So I think I have two comments. Interesting talk. One is keep in mind that all the AI model is population-based. They cannot do individualized. As we know in the causal inference, we cannot do individual causal effect statement because of you don't observe both of them. So best you can do is the population level.
Yeah.
So if you do the population level statement, sometimes you need to make a much stronger assumption to translate that statement into individual, which is the ChatGPT want to do. They'll give you individual answers, not the population level answer. So I think that's maybe the point. How do we translate individual level knowledge into, the population level knowledge, which all the model do, to the individual statement, which is the ChatGPT or those ChatGPT, the large language model try to give you, right? They actually the individual answer, not the population level answers. Have you given some thought on those issues?
Yeah, that's a great point. In fact, another way of thinking is that they're giving population level answers, but perhaps they're also sampling from the mode of that population. So let's say for this question, if there was like 90% of the world's papers or articles were written for the first relationship, L5 causing obesity, and maybe only 10% of the articles were written for the reverse relationship, ideally you would expect that LLMs, if you're doing some kind of optimistic decoding, they would always answer the first one, right? That they would answer the more popular thing in the population. But that's also not true. I think in this case, for example, it somehow answers the second one. But I think to your main point, that is a very hard question. I think the way some people interpret that question is like conditional effects, right? So just like in causality, we have conditional average causal effects, which are called Kate. It is possible to extract some kind of conditional information from LLMs by prompting, in the sense that I could give enough information about this particular individual in my prompt. For example, the fact that they already have L5 radiculopathy or some other details, which might move the LLM's probability distribution into a space which is conditional on this information. In that case, I can still get some more customized answers, which depend on this particular individual's information. But in general, I don't think it's possible. Like to the extent you can condition it using a prompt with some information, you may be able to get some customized answers. But yeah, for a particular individual, I don't think LLMs would be a good source of knowledge.
Right. So I feel like the language actually we're using have to be careful. Before, if your language you use like obesity cause something, so that's actually individual level statement. So A cause B, I mean everybody is the same, regardless individuals. And that's very hard to do. We know that our causal inference lecture, most you can do is population level, unless you make a very, very strong something like a constant causal effect, right? So I feel like maybe in the community, we have to be careful with the language we use. By bringing in the uncertainty in the data and also bringing in uncertainty in individual causal statement.
Yeah. So here, just to be clear, so the causal graphs we are constructing, the implicit assumption is that these are population level graphs. We are not saying it's an individual specific graph. So the idea is that if there is an edge between two variables, then there exists a significant fraction of the population for which that would be true. So even this obesity causes L5 is not an individual statement, it's a population level statement.
So maybe it will be helpful to actually quantify what is the population statement you refer to. Is 20% or 30% true with that statement? Yeah, that's very important, I think.
Right.
Yeah. Anyway,
we did not get into that detail. Yeah, it's a good point.
I think that's quite an important issue, I think, to exactly clarify the statement we're talking about, like obesity cause something. Like you say, that's actually maybe only 80% true in the population. But if you don't tell the model, they are just assuming everybody is true, probably.
Yeah, no, that's a great point. And I think we didn't do this in our study, but there is perhaps a future study to be done, which also looks at the effect strength or this probability of occurrence of the different kinds of relationships presented by LLMs, right? That'd be very interesting to see, like, do LLMs have a higher accuracy on the more population scale relationships, meaning they are at least satisfied by a majority of the population, versus these other relationships, or vice versa? I have no idea. It could be either opposite as well. LLMs are quite remarkable in strange results. But I think that's a great point. Yeah, we should probably think about doing something like that. Because actually, one more thing I'll say and quickly move on then. One problem that is still an open problem is confidence intervals for these kinds of predictions.
Yeah.
So in our paper, we did not do that. We just sort of did one shot inference. But if you want to use these results in practice, you would want that for each edge that is being produced, you get some kind of confidence interval, or you get some kinds of error bounds on the presence or absence of those relationships, right? So I think that's also is a very interesting open question on how do you get those kinds of statistical measures as well. There are some answers, like people say just ask the LLM 10 times and then do some average. Maybe that's okay. But I feel there's a lot more to be done to get better confidence intervals.
Yeah. I think that's pretty cool. So you mentioned how to use the large language model to give to quantify the uncertainty of the
Right.
causal estimation or to provide a confidence interval. I think that is very important. So that's what inference are doing in the statistics community. I think that's
Yeah.
pretty cool. And I have my sorry for interrupt for a long time. So I have my last comment about the large language model for causal discovery. So you have mentioned your experimental results, so including the two types of method. The first
Yeah.
type is the covariate or covariance-based method. So that
Right.
is I think that is data-driven, maybe
Yeah.
use the tabular data set to use the conditional independence test. For example, we use the PC algorithm to use the no
Yeah.
tiers, so like you early mentioned. And
Correct.
but if you ask directly to the large language model to orientate, the causal direction, I think what you are doing is like just information retrieval to like you are just doing a search and retrieval, I think within the pre-trained the languages, because
Yes. Yeah.
yeah, I think and I think the surprising result is even in a more complicated data set. I mean the is this data set. This is Pasic pain data set. So rather than the Tübingen data set, I think that is
Yeah.
more vertical data set. It's more
Right. Right.
focusing on
Yeah.
sub area. I think the GPT still outperforms the statistical test method, the covariate-based method, for a large margin. So the GPT-based method still outperform. I think that is a very interesting finding. So
Yeah.
because earlier you mentioned you talk about two very interesting examples. So you use the Julia Peirce example. So and you slightly changed your language. So
Yeah.
the rainy example you earlier mentioned from the outdoor to the indoor. So that is
Right.
a pretty interesting example, and you show the current in exploiting the large language model to do the causal discovery is not robust, because
Yeah.
yeah, when we intervene or when we slightly change the language into a less common language, for example, I believe that no previous text they are talking about the indoor, indoor status with outdoor rainy, that status. So that is less common. So you will find that the large language model it will lead to a wrong causal direction. And you have similar findings in your paper, like you change the length to diameters, and you find the causal orientating is wrong as well. So your new finding is in this more specific data set, the large language model could still outperform the covariance based method for a large margin. So I want to know, so how large language model they do the causal discovery, and why they could outperform, the algorithms like the PC algorithms, why the large language model they can perform so well. So I think that
Yeah.
maybe that is an unsolved problem, and everyone wants to know that. Yeah,
Yes. Yeah.
yeah, this is amazing, and somewhat it is some conflict findings. So I don't know
Right.
what either the large language model they use, they just doing the search and the information retrieval within the pre-trained data set, the language data set, or they have the counterfactual reasoning or the causal directing ability. So that is
Yeah.
I think one of the most important research question, and it is unsolved nowadays.
Yeah, I don't have a good answer. You're right. It is unclear. I'll make two comments. So one is they are doing retrieval, but I think
Yeah.
think of it as like approximate retrieval, which
Yeah.
means that if you ask the same question to Google, Google may not be able to answer it correctly. But
Yeah.
I think because they can do approximate retrieval over embeddings, even if your question is not exactly asked in the right words, maybe your words are different, or you can change the way in which you ask the question, they're still able to get the right answer. So somehow I agree they are kind of doing retrieval from their pre-training database, but because of their embedding space is so rich, I could ask the same question in multiple ways. In fact, I found that you can make spelling errors also in some of these things. And even then, the LLM is able to get what you mean, right? So I think that's one thing that maybe that has changed. Retrieval was always there, but this is like much more powerful
Yeah.
retrieval.
Yeah.
I think the
Actually,
second, yeah,
yeah, go ahead, please. Yeah.
the answer to your second question is, I think even though we are finding that in, let's say, the graph created by doctors in 2023, GPT-4 is still able to do well. I think the reason still is that that graph may not have truly new scientific knowledge. Right? The
Yeah.
doctors created it for Alzheimer's, and maybe they did it for their study, but perhaps all of the relationships were already known. Right? It was not like they 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 created new relationships by creating the graph. Actually, they encoded existing relationship by creating the graph, and then they did an experiment to find new relationship. So
Yeah.
I
Yeah.
think I agree with you. Maybe GPT-4 is good at giving you the background knowledge. So think of any science experiment, right? Think of physics or think of biology. Often scientists have some background knowledge, which helps them design the experiment. And then there's one new knowledge that they want to extract. My understanding is LLMs are very good. If you're a new scientist, LLMs are very good in giving you that background knowledge that you need. I don't think they will work if I have a completely new question to ask. Like, let's say some new disease has come up in next year, and then I ask something about that completely new disease. I don't think LLMs will work.
Yeah, I think you raise a very great point, which is even though the large language model can outperform in the most recent data set, but maybe they just when the large language model create a global global causal graph, maybe every local part it is existed for
Right,
the causal
right.
graph. Yeah,
Yeah.
and our team have just conduct another experiment. So we give a tabular data set to the large language model, but for each
Okay.
variable, we mark with a semantic information for each variable.
Yeah.
So if we switch the two semantic labeling, if we switch the two variable semantic information, we find out that the large language model will perform the performance will be, the result, the causal discovery result will also be switched. So
Yes.
which
Yeah.
means that when we provide both the text information and the tabular, the numerical information, the large language
Right.
model only focusing use the text information. So they are
Correct.
not conducting any conditional independent test. They just use the text information to orientate, to give the causal direction, to answer the pairwise causal, like what you raised, the A cos B or B cos A. So
Yeah.
they large language answer that question just by analyzing the text description, not conducting the conditional independent test. So that is
Yeah. Yeah.
what I found. Yeah.
Yeah. Very nice experiment. Yeah. In fact, I would imagine if you did not give the semantic names, if you just give the data, it'll
Yeah.
just fail, right? It'll be like random accuracy.
Yeah, just
Uh, so,
random. So if
yeah.
we mask the numbers, we just
Yeah.
but we keep the text description.
Yeah.
Large language model performance will remain the same, which
Yes.
means
Exactly.
it didn't leverage the numerical data, at
Yeah.
all. Yeah.
Yeah. Yeah. I think the real potential is in using both, but with different algorithms. So what if you could use the LLM with the text the semantic columns, and also use an existing PC-based or data-based method on the data. To me, a very interesting research question is, can you combine these two algorithms? Like, one idea I've been exploring is, suppose I'm running the PC algorithm, and at some point, if I find an edge that is not able to be oriented because of the data set, right? Because there's no such constraint that can orient this edge. Can I use the LLM only for those edges? And if I do that, can I also have some kind of confidence interval so that I should not accept every edge, right, from the LLM? I should maybe do some correction, statistical correction on top of the output from the LLM. Yeah. So to me, I think that seems the most exciting research direction, right? Like just PC was not enough earlier to orient all edges, but could we use the LLM in some intelligent way to make our existing algorithms more powerful? That would be very.
You know, if we just use data driven, if so the PC algorithm can just give a CP DAG. So which including the undirected edges, right? So some of the edges are not directed. So which means for some pair of variables, we don't know whether A equals B or B equals A. And a recent paper published in a workshop of SAML. So they find out that, so I think they first used the PC algorithm. They have some undirected edges. And then within this Markov equivalence class, they use the large language model to direct the undirected edges. Because we know that, because we know the additional text information. So we can leverage those information to help to orientate the the causal direction for those undirected edges within this Markov equivalence class. I think that is pretty good. But if we directly use the large language model to orientate all the edges, we cannot ensure that the obtained DAG is within the Markov equivalence class, via the PC algorithm. So it might be contradict.
Correct.
Thank you. I'm sorry to interrupt for so long. So go ahead, please.
No problem. I'll go ahead now. So we have about 20 minutes for the full session, right? 20 minutes left.
You just take your time. I think maybe we can go ahead for more than half an hour. So we have enough time. So please just feel free and go ahead.
Okay. So I'll conclude by also showing a result on full graph discovery. So far, we were just looking at pairwise discovery. So in this data set, the authors of the data set provided a 100-pair subsample, which meant that now there are a subsample of this large graph. But now we know there are only 50 correct edges and 50 non-existent edges. The question becomes slightly more complicated because now there's also a possibility that there is no edge. So we just add one more option called C. A causes B, B causes A, or another option, it's that no causal relationship exists. So just a slightly difficult task because there are 3 types of answers. So here we find that prompt matters. So the original authors of this data set, the neuropathic pain data set, 2 et al., they had also tried ChatGPT because I think they were also curious whether it'll work. And they found that it was not working that well because I think their recall was 0.12 and the final F1 score was only 0.21. But interestingly, we found that if we use the same prompt that we were using for the pairwise data set and even Tubingen, somehow we got much higher precision and recall. So if you look at the GPT-4 or GPT 3.5's performance, its F1 is about 0.68, which is about 3 times higher than what was previously reported using LLMs. So I think the minor finding we have here is that prompt also matters. I think just like Andrew was saying earlier, that there's a difference between population scale and individual relationships. I think at the very simple level, there's also a difference in how you condition the probability distribution of the LLMs, right? Which is what prompt does. And there is a possibility that for different applications, you may want to use a different prompt so that you get a much better accuracy. But then, at least what we have found, which is impressive, is that we did not change our prompt, right? We were just trying the same prompt across data sets. I'll show you one more data set, which is an atmospheric science data set. And even here, we found that we are getting accuracy that is either comparable or better than existing database methods. So this data set was released, I think in 2021. So perhaps it was still in the training set, but it's still a very new data set. There's only one publication on it in 2021. So it's a 12 variable data set and 48 edges. And here we take the entire data set. So our goal is causal discovery on the entire data set. And the variables, again, I mean, I did not know many of them. These are very specialized variables like meridional and zonal wind, net shortwave and long wave flux, etc. And the metric that we're reporting here is NHD. So think of it like SHD, like structural Hamming distance. Lower is better. So it's kind of the error in the graph produced by different algorithms. And again, we find that GPT-4 is able to get an NHD of 0.22 on this graph, which is significantly lower than existing best methods tried on this data set. So now let's quickly just answer this question. We've already had a good discussion on it, but is it simply retrieval, right? As Hao-Sheng was saying. Is it just collecting some information from the web and just giving you an answer, right? So for that, we did a memorization experiment, which is that now instead of asking the causal question, we will just ask it to complete the data sets that we have for evaluation, right? So for the Tübingen data set, we can say, oh, I'll just give you the first pair and age of the data set. And now you have to guess what comes next in the data set. If the LLM is able to do well on this task, then that suggests that it has literally memorized the data set, right? It's not doing causal inference. It just has all the data sets prepared already. So at least for Tübingen, we did find that it has been memorized. So for example, there's a 61% probability that if I just ask it to predict the next cell, it'll give a good answer. But its accuracy on rows is very low, 25%. So by row, I mean it has to also produce the arrow at the end. Okay? So it's true that it has been memorized, but what we found for the other data sets was that it was memorized less. I think the comparative number for the medical data sets was much lower than 61%. If I remember correctly, it was 20% or even lower. And then for Arctic science, it was even lower, right? So it does say that, yeah, there is some amount of memorization happening, perhaps smaller for less popular data sets. But we can never rule it out because we don't know, right? These language models are trained on so much data that I think we could assume that probability of D is always true in the sense, like, let's assume for a second that all these data sets were memorized by the language model. To us, what's really interesting still is that even if it was memorized, even if it was a part of the training set, these large language models can process these data sets so well that they have a very high likelihood of Y given D, which means that if the data set was in the training data, what is the likelihood that you'll give correct answers based on this data set? And I think that is the real answer here, that these systems are significantly better than any existing retrieval system that we had before. And they are able to transform text from the user to match it to whatever knowledge that they have learned as a part of the training process. So yeah, I think formally, I think this is a better way of thinking about LLMs. Rather than thinking about whether it's in the dataset or not, I think it's likely that many things are. But the more impressive part is that getting the answer from such a vast amount of information is also a very hard question, right? And somehow LLMs are very good at that. Even though they've been trained on billions of documents, they can always retrieve correctly questions from multiple domains. But as Hao-Sheng was also saying, right, it's still not just that. Like, there is also some amount of, I would say, reasoning happening, because there are certain answers it gives which show us that maybe there is some amount of perhaps, I shouldn't say reasoning, but some amount of non-trivial retrieval happening, right? Which is not just based on retrieval. And I'll show some examples as we go on in counterfactual reasoning also. So yeah, I think I would say it's mostly approximate retrieval, but there is still some other kind of reasoning happening that we need to investigate more. So for example, it can do transitive relationships, right? So if it knows that A causes B, it can predict that. And so yeah, if you know that A causes B and B causes C, it can predict that A causes C or C cannot cause A. So those kinds of things GPT-4 can do, and I think people still don't understand why that is the case. So very quickly, I think there are other tasks we also tried. You can look at our paper for details. So we looked at the task of suggesting missed backdoor variables or missed confounders. LLMs do a reasonable job here. They give you a bunch of suggestions. You can check which ones are correct. They can also help you suggest an instrumental variable or a negative control. Again, think of these as assistants to a causal inference researcher. In that sense, they are very good. And we are trying to build a library called PyLLM that helps people augment their analysis using LLMs. So we are still thinking that people will be driving the analysis, but they can do calls like these, as I'm showing, right? Modeler.suggest confounders. So if they had missed a confounder, maybe this will be an interesting exercise for them to check. Or they can even suggest harder things like negative control or robustness variables to check for. And I'll just give you a peek into what may be possible in the future with these kinds of LLMs. So look at this question, right? This is a question about some toy shop owner. They might have some sales data. So they just put that sales data here. And they might have shown some ad in December and their sales increased in December, right? So we tried asking GPT-4 if it can also help in these kinds of real world scenarios. And so now we are asking GPT-4, first tell us, hey, why were the sales increased in December? Was it because of ads? It's a causal question, right? And second, we are also asking what confounders might be there. And so here, if you see that GPT-4 is reasonably good. I mean, it's giving you different points to consider, which might be confounders for this relationship. So it gives seasonal variation, where December is typically the holiday season. It also says there might be economic factors, there might be competitors, and so on, right? So it just gives you a big list. The point is that this is a very plausible list, and to someone just starting out in economic analysis, using GPT-4 as an assistant can be very useful for them to think about hypotheses, to think about possible confounders they might have missed. So implications for research we already discussed. We want to combine existing graph discovery algorithms with LLMs. And there's already some work that I'm mentioning here. You can take a look. And I think the open questions are two. One is, how do we make it closer to statistical inference and get confidence scores? And also think about end-to-end learning, because if discovery is also happening in an automated way, maybe there is some potential to combine causal discovery with causal effect inference, or combine causal discovery with causal prediction, and try to see if you can build end-to-end algorithms that could go from data to causal answers. And of course, I mentioned the implications for practitioners. You can actually start using LLMs with existing tools, almost like a fluid interface. So the takeaways from the first section, I know we are late on time, but I'll quickly mention the takeaways for the first section and then move on to the second section, which I'll do very quickly, is that LLMs enable knowledge-based discovery, and you can think of it as approximate retrieval, but the impressive part is that it's retrieval on almost all known human knowledge. They have partially memorized data sets we have tested on, but I think the key part is that even with memorization, they're able to generalize so well across domains. And I think the open questions are really how to make this much more reliable. Right now, I think there's a lot of interest in this topic because the results are surprising, but I don't think they are reliable to the level that you can actually use them properly in a system. So reliability, I think, would really be a very important research topic for these methods. Okay, let's just quickly move on. I think in the interest of time, let me introduce this next topic that we also investigated in the paper. And then we'll come back to some questions that you might have. So far, I think it was nice to see that LLMs can construct graphs. We then moved on to the second topic, which has been also a big challenge for causality, which is individual level causality, right? So now let's come to Andrew's main question, right? So there is this kind of event causality. So far what we discussed was what is called general causality, where you're just interested in what is the effect of smoking on lung cancer, right? It's a very general scientific relationship. You just want to know the population level answer. There is another kind of causality, which is called event causality, which asks questions about a particular event. So it could be things like the ball hit the wall. That's a very specific event, right? This ball hit this wall. Now I can ask questions like, what caused the ball to hit the wall? Right? Maybe the answer was gravity. So event causality has been studied for a long time. And there's a book actually by Joe Halpern called Actual Causality, which tries to formalize causes of events that happen. But what we found was for many years, it has been available. This knowledge has been available, but systems have not been built, or sort of more practical algorithms have not come out of this field. So let's just look at first actual causality. So I'll give you a brief overview of this event-based causality, and then we'll see how LLMs actually help in answering some of these questions. And actual causality actually comes up everywhere. So this is an example of, again, an electronic medical health record where this person is suffering from some low-grade pancreatic neoplasm. And what was possible without LLMs was language analysis. So you could ask, what issues is this gentleman suffering from? What procedure did he undergo? But causal questions were not possible. People were not even thinking of causal questions, to be honest with you, on these kinds of data sets. You could ask things like, what other tests would you recommend? What may be the likely diagnosis and why? Or if the blood sugar returns 200, how will your diagnosis change? Right? These are questions that doctors talk to each other about, and they can answer these questions. But it was very hard to even ask these questions in a causal way before. But again, what we are finding is that somehow GPT-4 is able to answer these questions. Again, we don't know how, we don't know, we doubt that it's actually causal reasoning, but they're able to answer correctly. And if you're interested, you can look at this book. It has many such examples of these questions. But let's take one of the examples from their book. So this is a real world patient, and they describe some events about this patient, and they ask, what do you think accounts for this difference in mortality between two types of patients, right? So one who have white blood count low between some time, and the other who were measured at some other time, and they also had a low blood count. And they're asking, why does one group die earlier than the other? And interestingly, GPT-4 is able to give an answer that seems very intelligent. So it is able to find out that the timing of the blood samples in early morning might be a confounder. Right? So it's saying that the reason that their samples were taken in early morning means that they were probably admitted in the hospital, means that there was something serious, and that's why you had to take it at such a night time. And of course, they also give some other reasons, but basically that was the main reason. And so this is a very impressive answer if you think about its implications for reasoning. And then there are other questions, I think. So this is a question from a test, a medical test that US doctors have to take. It's a multiple choice answer. And I think based on just this report about a person, some 12-year-old girl, you're supposed to say which test will be the most abnormal. So this description does not mention anything about that test or that result, right? It's just giving us some information about this patient. And the question is, if we give that test, which of these tests will be the most abnormal if we give that test? to this person. And here also somehow GPT-4 gives the right answer. And I was like, what? How is this possible? Like, this is expert knowledge. So maybe again, the same thing is happening, that GPT-4 has just memorized all the test questions. It has just memorized all the exams for medicine. And that's why it's able to give the correct answer. Or it's something interesting, right? So we did the same thing for the second part of the paper as well. We said there's a lot of information available about GPT-4. People are claiming it can answer medical questions. Let's just study it in a much more formal way. Right? And specifically, we want to study it in a causal way. We want to set up a causal experiments with causal data sets and understand whether text reasoning is possible, or is it still retrieval, right? Is it still retrieval from existing text data sets? And so here, as I said, now we have to find different kinds of data sets, right? Because we are interested in actual causality now, which is like, for example, Bob, who might be an employee of a coal plant, has been smoking cigarettes, and then they get diagnosed with cancer. We are asking, did Bob smoking cause their cancer, right? We are not interested in smoking in general, but only for Bob, we want to answer a question. And as Andrew was saying earlier, you can see how this is so hard, right? Because now it's not just a relationship you can average over multiple data. This is a specific relationship about one person. And I think there are other questions as well. For example, a doctor washes their hand before surgery. What would have happened if the doctor had not washed their hands? I think one thing that you will see is very apparent here is that somehow you need some external world knowledge even to answer this question. Because a doctor washes their hands before surgery, sure. What would have happened if they had not washed their hands? Many things could have happened, right? Water may not be used. Some patient may get infected, or many other things can happen, right? But just the fact that we are connecting a doctor to a patient means that we have some ground knowledge about the doctor washing their hands in the context of a hospital, right? Because otherwise, the doctor could also be washing their hands before surgery in some other context. But I think we're able to understand this context because of world knowledge. And our question is, if as humans we can understand this context, can LLMs also understand this kind of context? More formally, it is called causal frame. And that's what I'll come to. The reason event causality is hard to formalize is because it needs a causal frame. Think of the causal frame as a graph, but it's often not explicitly the graph. I think it's also about the background knowledge. It's about the assumptions that are implicit in text that you also have to uncover. So let's say this is a question I ask you. Suppose Alice reaches out and catches a passing ball. The next thing on the ball's trajectory is a solid brick wall. So now we understand this question, right? Alice caught the ball, but even if she did not catch the ball, there would be a brick wall that would stop it, right? And the real question is, what caused the window to be intact, which was after that wall? So as an AI agent, I can answer many things, right? I can answer gravity. It's always correct because gravity is always in play. Gravity must have affected the ball's trajectory. So gravity is a correct answer. Newton's law of motion is also a correct answer. Newton's law of motion is the correct answer for any physics question about balls and windows, right? But the right answer here that most humans would agree is Alice's action, right? Because Alice reached out and caught the ball. That is what we expect AI agents to answer. So this just goes to show that causal frame itself was so hard for models before that we would not even try such tasks to train models for, right? But somehow, as I'll show, LLMs are able to understand the causal frame, which means they can understand the implicit assumptions that human beings make when they ask questions like these, right? So here, for example, the implicit assumption was that gravity, Newton's law of motion, physics, etc., they are not the correct variables in this problem. So do not make a graph using gravity and Newton's law of motion. Instead, make a graph using Alice, ball, Alice's action, and so on. And so before going into LLMs, it's important to understand the steps that any agent has to follow to answer questions correctly. It first has to determine the causal frame, which is determining the variables that are important to answer this question, which are not given in the question, by the way, right? Many variables could be outside this question that you need to include. Second, then you have to determine the relevant definitions of causality. So today we'll use some simple definitions of necessity and sufficiency. But as I mentioned, there are much more formal definitions proposed by Halpern, which you can look at if you're interested. But for today, we'll just look at two simple definitions and try to evaluate LLMs. The first is necessary condition. If Alice had not acted, would the window still be intact? That's our first condition. And sufficient means if Alice acted, would the window always be intact, right? So, I mean, this is the same as necessary and sufficiency in logic, right? We are just trying to ask if Alice was a necessary cause or Alice was a sufficient cause or both, right? So that's what we'll try to do. And as I mentioned, if you don't give the causal frame, right? If you don't do step one, there is no algorithm today that can solve this problem. All of the existing algorithms proposed in actual causality assume that the human gives that causal frame, right? So the human being gives you all these variables and also the graph among those variables. Then existing algorithms can solve this task. But I want to make it clear that without that human interpretation of the question, there is no algorithm today that can solve this task. Can LLMs do it? Let's find out. So we'll do counterfactual reasoning on these kinds of questions, which is a very simple task. And actually, counterfactual reasoning is the building block to even answer necessary and sufficient causes, right? So let's just first look at counterfactual reasoning, and then we'll move to necessary and sufficient causes. The reason I say counterfactual reasoning is the building block is because it's kind of simulating alternate outcomes. So it's closely connected to the necessary cause that we will investigate, right? But here we are only interested in if I slightly change the situation, if I slightly change some variables or text in my question, how well does the LLM still give the right answer, right? So we'll start with this. It's a building block. But as I'll show later, necessary and sufficiency can be defined as just concepts over counterfactual reasoning. So we were lucky here as well. There was already a data set that was released. It was called the CRAS Counterfactual Reasoning Benchmark. And it had questions like these that I had just mentioned earlier. Like a doctor washes their hand at work. What would have happened if the doctor hadn't washed their hands? The options are given. You just have to choose between one of these three options. Right? And to answer this question, you can now immediately see that the model has to know that there is some connection between washing and infection. But note that infection has never been mentioned anywhere in this text. And then there are other questions as well, like an oil tanker sails across the ocean. What would have happened if the oil tanker had broken up? Again, you need to know that oil tanker breaking up in an ocean means environmental pollution. So what we find is that GPT-3 and other models were already evaluated by Froberg and Binder, and they found that LLMs were not really doing that well. I think the best accuracy they got was about 72%. We took exactly these questions without any prompt tuning. We would just give exactly the question and the options to the modern LLMs that have been released. And we found that the accuracy again has increased significantly. So GPT-4 gets about 92% accuracy on this task. And again, note that this is unlikely to be memorized. I think it has been very recently released. In 2022 was the paper. 2021 was their release on GitHub. But again, it was not a popular data set in 2021. And just for noting, human annotators get about 98% accuracy. So we are still far from human accuracy, but it is truly surprising how GPT-4 is able to answer these kinds of questions as well. One answer, again, is like Hao-Sheng was saying, it's retrieval, right? Maybe in its embeddings, this question was not asked. It is true that the training set may not have this question, but in its embeddings, it has learned that ocean, oil tanker, has to be connected to to environmental pollution, because there might have been many news articles which said ocean, oil tanker spill, and pollution. Right? So maybe that's what it's doing. It's just able to connect existing articles and the concepts and then apply them to new situations. But also, it's not always kind of memorizing. So if you look at this answer, a man catches a ball. What would have happened if the man had caught a water balloon? I think the right answer here is that he would have caught the ball. Sorry. So what would have happened if the man had caught a water balloon? I think it's probably answer B or answer D, right? But the reason I'm hesitating here is because even I don't know. This data set, if you look at this question, a lot of things could have happened, right? And this is exactly what, if you see the answer from GPT also suggests, like it chooses that it's uncertain between B and D, right? Because B could also happen. He would have got wet because he caught the water balloon and the water balloon burst. And D is also possible because the man is a very good catcher. He catches the water balloon and it does not burst, right? So again, this is kind of eerie, right? So it's sort of suggesting that it's not just memorizing. If it was memorizing, it would have just said answer D, which is the correct answer in the data set, right? But at the same time, it also sort of does some stupid stuff, I would say. I would not even say silly stuff. Like this is completely stupid in the sense that the question was that what would have happened if a man had walked on a bed, right, instead of a street? Now, causal frame comes in again, right? Causal frame would say that walking on a bed means that a bed is in a room and a room is in a building, right? It's not physics, it's not a law, but it's just like the causal frame that human beings construct when they write in natural language. However, GPT-4 has no idea of that, so it assumes that the man is walking on the bed on the street. So they feel that this is not a good way of transport. You should not walk on the bed. You will not reach your office. So again, I'm just trying to show you these examples just to communicate two things here. One, getting the causal frame is very hard problem. It not only requires reasoning, it also requires understanding what human beings are implicitly meaning when they write some text, right? That's the first point. So it's not just about causal reasoning, it's also about knowing the world knowledge, knowing the implicit assumptions in text. And I think the second point is that even though this task is so hard, we are seeing evidence that language models can do this task. And in fact, they're the first models to do this task at all. Like there was no model before that could do it. Now let's move to necessary and sufficiency, which is the real deal. I mean, what I showed you earlier was just a simple task. But if you really want to address event causality, we have to see if necessary and sufficiency is a concept that is captured by language models. So now let's just define this formally. So necessary here means if an event C does not occur, the outcome event E will not occur. So you have to do a counterfactual about what would happen if the event C does not occur. Sufficiency says if an event C occurs, then the outcome event will occur, right? So now it's a counterfactual about changing all other variables. Doesn't matter. You change all other variables, as long as event C happens, then outcome E will occur. And sufficiency is harder, as I mentioned, because you have to know what are all the other variables that should be changed for this relationship. For evaluation, we constructed our own data set. There was no data set available for actual causality. So we looked at books of Halpern, Joe Halpern, and we found these 7 types of tasks that event causality literature looks at, right? So each of these is a different kind of twist on the problem. So for example, symmetric overdetermination has multiple processes that lead to the same outcome. So now it's interesting, right? Because you have to think about that maybe all of them were sufficient, but none of them was necessary, right? Because even if one did not happen, the other would have happened. I won't go in details of all of them. If you're interested, you can look at Joe Halpern's book. But our motivation was to create a diverse enough data set such that we can cover all kinds of situations. And here are some examples from Kuefner et al. We also used Kuefner's work to construct this kind of terminology. So this terminology comes from Kuefner's book, Kuefner's PhD thesis, sorry. And so examples are like these, right? The first overdetermination example would be Alice and Bob each fire a bullet at a window, simultaneously striking the window, which shatters it. And now I will ask, is Alice a necessary cause or is Alice a sufficient cause? Right? That is the setup of this data set. So here we found an interesting result. GPT 3.5 failed on this task. We found that when asked to determine the necessary cause and the sufficient cause, the accuracy of GPT 3.5 is about 46%, which is worse than what you would do if you were predicting randomly. But GPT-4 somehow gets 86% accuracy. Again, no, I have absolutely no idea now how it's able to do it. Perhaps the answer is that it was memorized, but I'll show you one more result very quickly that we did. But I think this was the biggest surprise for us, because these are questions that require reasoning over the text, plus understanding many other factors that are implicit in the causal frame. But somehow, even for sufficiency, GPT-4 gets non-trivial accuracy on this task. And again, I mean, I can show you some examples where you can also see that there is some amount of justification given for why this is the correct answer. So that's quite interesting. But sometimes it also gives you errors, right? So LLMs can also obviously get confused. As I mentioned, they are not reliable. So in this case, I think one of the answers gets incorrect because they are confused between the definitions. But the most interesting part was that in this case, at least, we were able to create a data set which was completely new. And the way we did that was we perturbed the details in the original data set and adapted it for scenarios in a chemistry lab. So now, rather than Alice, Bob, and balls hitting windows, we created a completely new world where there would be, for example, a fire in the chemistry lab, a can of water would douse the fire, agents X and Y both spray a can of water each, dousing the fire, right? So it's kind of the exact thing about balls hitting windows, but now we have completely changed the language, completely changed the words and names of the agents, right? And now we'll ask exactly the same question. Is Agent X a necessary cause of the fire being doused? And is Agent X a sufficient cause of the fire being doused? And what we find is that, interestingly, the accuracy increases. It's slightly higher for novel examples. GPT 3.5 again fails, but GPT-4 is able to retain its high 85, 86% accuracy, even for these novel examples. This suggests that it's not just retrieval. There is some amount of reasoning or process information also stored by the LLM, right? So now I think my current hypothesis of how LLMs work is that when they read text like these, for example, I'm sure they have read Joe Halpern's book. It's a very popular book, so it must be in the LLM's training data. But when they read examples like Alice and Bob and shattering the window, they're not just remembering Alice, Bob, and shattering the window. They're able to somehow also create embeddings of actions being taken and what might be the sequence of actions or the reasoning behind actions. And so even if I now change the words, if I change the words from Alice to Bob to X and Y, or from Windows to fire, they're still able to make the same conclusions because I think they're storing much more than just the words. They're somehow also storing the meaning of those actions. That's my current hypothesis. All right, so I'll conclude now. And if we have time, we can take some questions. On actual causality as well, we are seeing substantial improvements in LLMs. GPT-4 can do something that there was no algorithm before that could do it, which is understand scenarios and identify necessity and sufficiency. We also tried other tasks where GPT-4 fails, which is, for example, normality task and responsibility task. So you can see the paper for details, but actual causality is still much harder. I think it's a very hard problem. It's still interesting that LLMs are able to even do some parts of it. And so I think in the future, as I mentioned, we want to know not just what LLMs can do, but also how they can do it, right? So can LLMs do causal reasoning? I think it's an open question that we need to solve, and maybe we will solve in the next few years with more concrete evidence. But also, while the scientists are solving that question, if you are a practitioner or if you are a researcher in causality and you want to apply the methods to new domains, I would suggest use LLMs, right? Even though there's no proof that they can do causal reasoning, there is enough empirical evidence to show that they're actually useful in causal inference process. So if you are interested in applying causality to applications, I would suggest exploring LLMs, suggest looking at how they can give you a graph, how they can give you a causal frame, how they can help you create initial analysis that then you can fine tune. But as I said, what's not changing is that we still need rigorous analysis, right? So we still need to have guarantees, we still need to have confidence intervals. And so that's something I hope will happen in the next few years. And there are some research questions that have come up because of LLMs. Maybe I'll put that as the last slide and open up for questions.
Yeah, I think thank you so much for the exciting talk. And I think this talk is very easy to follow, and we get a lot of insights from this great talk. So I want to ask if there are any questions from any of our audience.
Yeah, can I ask a question about the some of the conclusion part of it?
Sure.
Yeah, so I think one of the things that that I'm very interested in is to combine the large language model causal reasoning capabilities with kind of like a more traditional statistical based causal discovery tools. I don't know whether you have used like a tetrad.
I know tetrad.
Yeah, or some of these like a causal learn or something like that.
Right. Yeah.
To kind of like to give these kind of like these more statistical tools better common sense capabilities, and also like a meta-analysis, and also suggesting, like you said, like a causal frames. I'm wondering, whether there's any attempt in, again, from both a process point of view and also from a capability point of view, combining the large language model capabilities, with these traditional causal discovery frameworks.
Yeah, so I think there have been lots of papers in the last year, just like Hao-Sheng was saying, there's an ICML workshop paper. I've also written a few follow-up papers looking at how LLMs can be used for causal inference, right? In the sense, can they give you a backdoor criterion directly? So not just doing causal discovery, you can also find the backdoor criterion. But I think your question was broader, right? So I think let's make it in two parts. The first question is, can we combine existing algorithms like tetrad, PC, and so on with LLMs? So with Hao-Sheng's question, I answered that part, which is that yes, we can do it. And today, even if you search in Google Scholar for these keywords, you will find that there are many papers which are trying to do that. Either they use the LLMs as a prior. So if you have a score-based method, then you use the LLM as a prior and then apply the score-based method to find a good graph. If you have more CPTAG-like based methods, constraint-based methods, you first apply, those constraint-based methods, and then after you can apply an LLM to refine those answers, right? So I think that part is happening. And then you can also extend it to backdoor variables, as I said. What I've seen less of is the second part of your question, which is about causal frame, or sort of using the LLMs in a way to both interpret the causal question that someone has and also try to answer it using some formal methods. So that, I think, Richard, if you're interested, would be a very interesting direction to take. So somehow what I've observed is we published this paper last year. I think a lot of people have done work based on the first part of the paper, which is causal discovery. But I haven't seen so much work on the second part of the paper, which I think is even more important because it applies to practical situations, right? It applies to reasoning over text. So yeah, to answer your question, I haven't seen a lot of work, but I think it'll be very useful to think about scenarios in which the LLM could almost become like a interface for people to ask causal questions, and also for them to help formulate those causal questions in a formal way. And then I think that can be given to tetrad, or it can be given to actual causality algorithms or other kinds of formal principled algorithms.
Thank you very much. I think on the second part of it, I also was thinking that when we look at the intrinsic mechanisms that large language model can reason, from a causal point of view, there could be a certain type of almost like a prompt, right? Like a specific causal framework prompt, which allows that when you are making like a critical decisions or making these kind of like analysis. Like for example, one of the things that I have seen in the past is that, like the theory of mind type of problems, where the Sally and type of stuff,
right,
which actually some of these most recent large language models like GPT-4 actually exhibit pretty good the theory of mind capability, which kind of like implies that these large language model for some reason has internal like a causal inference capabilities, right? To kind of like construct some counterfactuals or construct some type of causal graph when it's try to reason about a future event or a prior intervention or something like that, right?
Right.
But if we can put that in a kind of like a more systematic and reliable way, then we can put that framework into like a planning or reasoning or this type of kind of like a more, like for example, if you want to make a detective work or making like a put something that in a legal term that is acceptable to a court or something, then you want to make sure that your evidence and reasons have the rigor of I mean, at least doesn't bullshit, right, or something like that, right? Which basically means that you have to have certain necessity, causality, or some type of causal graph relationship that can be shown to be valid, right? So I'm thinking that if we have that in the large language model, we can put that into these tools or applications that make it much more reliable and kind of like rigorous.
Yeah, I think is already happening in other fields like logic, propositional logic, first order logic, and I think it'll also happen in causality. We are also working on some work, but I really like your point because see, if you think about it, right, we can use LLMs for what they are good at, which is interpreting natural language, interpreting people's questions, and then use these formal tools to do the actual work. Right? That way we get the best of both worlds. The LLM is great because now people can ask any question and the model understands them. And because now we are using the formal tools for the actual processing, we also can give guarantees, right? So I think in the specific context of causal reasoning, a very interesting direction is that we only use the LLMs to parse the human's question and convert it into some formal language, right? So let's say the language could be the graph structure, it could be the do calculus language, whatever it is, right? If we just use the LLM to convert users' question to that formal language, then we can use all the rules from UDA Perl and others to compute a correct answer to that question. And then we can again give back the answer in text because the LLM can rephrase that answer for the user. So I feel rather than LLMs doing everything, this idea where we use them as an interface to construct formal statements, but then those formal statements are actually solved by a system, a reasoning system. I think it makes the most sense. Like I think that's how things will progress. And it has already been happening in logic. So now there are many papers in first order logic, propositional logic, math, theorem proving, geometry, all of these fields. I've seen papers which combine this neurosymbolic way of reasoning where the LLM is doing just the translation from text to formal propositions. And then there's a separate theorem prover, there's a separate solver that's solving those problems. So yeah, I think Richard, you're spot on. I think this is, I think in some sense, the right way or the future of how LLMs will be used. But yeah, I think we need to still sort of solve some robustness issues in how LLMs can be used for these problems.
Thank you very much. Really enlightening talk.
Can I ask a question?
Yeah, sure.
Hello, Amit. I'm Ihan. So I have a question on the fifth research question you put here because I'm working on a human AI interaction project. We're trying to make the AI to ask questions, like structured interview to human, so that it can extract some intuition and inspiration from human. So two questions, maybe like there are actually one, but maybe two ways to ask it. One, do you think? What is your take on the general, a better way of human language collaboration for decision, or causal type of task? The second question would be, how do you think of our approach, to let AI to ask more questions rather than only give in answers? Yeah. Thank you.
Okay, I see. Yeah, so I think the first part is very similar to what I answered to Richard. I believe LLMs can help in understanding what the user really wants to do. Because often, except scientists, right? Most people, like a shop owner, as I gave an example, right? The shop owner's revenue was increasing and they wanted to know whether it was because of the ad. I think the first time they'll ask that question, they may not even use the word causal. They would not know what a causal effect is. So they'll ask the question in some simple way. Maybe they'll ask, why did my revenue increase? Something like that. So I feel LLMs have a big role to play in converting those kinds of English statements to understanding that's a causal question. So therefore, we need to create the graph. We need to create the proper formal statements for this to be interpreted, right? So there, I think that's the answer to your first question. That yeah, I mean, using LLMs as interface agents and then using these formal tools as background processing gives you the best of both worlds, right? But I think the second part is also important, which is what you're doing, is that we also need to ask some questions back to the user. Because the first question might be completely vague, right? And it is not clear that you can always get the correct answer if you just assume what the user is saying is correct, right? So I'll give you a concrete example in causal inference. Maybe it'll apply to your setting also. But in causal inference, what happens is the user will start with, oh, I want to calculate the effect of smoking on lung cancer. Here are the variables that I have in my data set, right? If the LLM just takes those variables, gives them to do calculus, and then gets back the answer, that's not enough, because the first thing the LLM has to check is whether the data set is complete, right? If they have missed a very important variable in the data set, the LLM actually should respond back that based on my analysis of scientific papers, there are other confounders also, right? So these are the confounders that typically are between smoking and lung cancer. Are you sure you don't want to include them, right? So I think that's a very useful question that the LLM can ask. And that will also help the user make their analysis better, right? Another example could be graphs, right? The user gives them some graph. The LLM could say, hey, one of your edges is wrong. Like based on at least my approximate retrieval, one of your edges is wrong. So then the human has a choice to correct that edge or not. But that has to happen. Like if that does not happen and only the LLM processes the user's first question, I don't think we'll be utilizing the full capability of what LLMs can do.
Okay, thanks.
Yeah, I also noticed Kausa Ahmed from CSU, so he asked very interesting questions. So maybe Kausa Ahmed, could you open up your microphone, maybe have a discussion with the speaker?
Thank you. So
yeah, go ahead.
Yeah, thank you very much, Mr. Amit Sharma. Actually, I want to know the causal effect. We know the confounder effect is very important for causal effect. So actually, how could we reduce confounder effect in NLM? Thank you.
Can you say more? So you want to remove the confounder effects in LLM's training or the answers they give?
Not remove, just how can we reduce the confounder effect?
Can you give an example of that effect?
Like you talk about the cancer patients. So for those, if you give any example from here.
Oh, I see. So I think the example I was giving for that cancer patient, or maybe this confounder, we can take a look, is more that existing NLP approaches tended to have some kind of confounders that would not be taken up. But actually, LLMs like GPT-4 are able to identify those confounders. So in this case, the confounder was the time at which the sample was taken. And actually, if you ask GPT-4, it is able to provide you that confounder. So the way I see it is that these advanced language models can be used to reduce the effect of confounding on existing studies, because you can actually ask them for the potential confounders in any planned study and use that information to decide if the number of variables you have is enough or not. I haven't found that GPT-4's answers itself are confounded that much, but it also depends on how you ask the question. I think that's my message, right? Sometimes it can just be unreliable and give a wrong answer, but I don't think that's because of confounding. I think if you ask about confounding, it actually has a much good response rate of giving you some actual confounders in a problem.
So this situation is also the major issue for LLM, for the causal reasoning. Okay, thank you.
Yeah, thank you for the great question as well as the answers from the speaker. So I just wonder if there are any more questions you want to ask for our speaker. Okay, so since the limited time, I will give a quick conclusion of the Dr. Amit Sharma's great talk. So I think the Dr. Amit Sharma, so he began with several exciting toy experiments and reviewing the unstable feature of using the large language model to conduct the causal tasks. So I think that is also served as an interesting future research direction. So how to improve the robustness when using the large language model to do the causal discovery or the causal effect estimation tasks. And I have one comment to add with Dr. Amit Sharma's the last slide. So I think he gave several wonderful future research direction. And because I'm doing the causal inference, so from the statistical view, so we know without statistical assumption, we cannot do the causal tasks. So which means that, for example, when we doing the causal inference, so when we estimating the conditional average treatment effect of just for brevity Kate, when we estimate Kate, we need to have some assumptions. For example, if you use the Rubin's potential outcome framework, we need to make assumption called unconfoundedness or ignorability. It assumes that there's no confounders. So similar assumptions you need to adopt it when you doing when you adopt the Julia-Peirce structure causal model. So you need to assume that there's no latent confounders. Or when you also similar assumptions you need to make when you do the causal discovery, you need to make the assumption that there's no latent or no hidden variable. But in reality, so those assumption is really hard to be satisfied in the real world cases. So we know that and I just wonder how large language model can solve the unmeasured confounder or the unmeasured confounding issue. So that is exactly the question raised by Mr. Kausar Ahmad from CSU. I think large language model, it provides a way because it have a lot of world knowledge. So it can use the world knowledge to fill the gap of the unmeasured confoundings within the limited observational data. So we know for every observational data, we may have some unmeasured confounders or hidden variables. And I just wonder if we can use the large language model to fill this gap because it have more world knowledge in the pre-trained text. So I think that serves as a very interesting topic. And for responding the audience questions at the end, so I think Dr. Amit Sharma gave a very grateful framework for how to leveraging the large language model to doing the causal tasks. So I just take examples to showing how the large language model doing the causal discovery. So Dr. Sharma gave 2 ways. The first is to reduce the possibilities of the DAGs within the Markov equivalence class. So to how to reduce the possible DAGs within this Markov equivalent class. And second is to using the large language model to provide a prior knowledge when you're conducting the causal discovery. I think that is a great direction. And that is and both direction is extracted from the most recent research paper. And I think, yeah, some of the audience can follow this way to conduct the follow-up researches. So for the causal inference, we know that Zhi Jing, who is from a doctor from the MPI, so supervised by Professor Bernard Shukov. So she adopts the causal engine from the Julia-Peirce and to use the chain of thought to to give the answer of the causal effect estimation using the chain of thought of the large language model. So, for example, you need to use the collected statistics, the prior known causal diagram, and as well as the do calculus formula as your input to get to recognize the statistical estimate or the causal estimate that we need to estimate, and then how to estimate that to using the Julia-Peirce do calculus. So several researchers have explored to use the COT or even POT to to let the large language model can accurately estimate the causal effect. And meanwhile, oppositely, so how to use the causal way to enhance the large language model, that is another branch I think is very important as well. We know that, like Dr. Sharma explained, the current transformer-based large language model is aims to predict the next token. So which is not a causal way to think. Because when human beings speak, we are not just speak to predict the next token. Instead, we have the causal structure when we speak or when we give a talk. So I think that is also interesting research direction. So how to leveraging the causal to improving the robustness or the explainability of the large language model. So I think, yeah, so Dr. Amit Sharma's talk give a very clear explanation for both ways between for the intersection of the causal reasoning and the large language model. So I also organized a workshop together with Professor Bernard Shukov at the NeurIPS 24 to continue such discussion. And yeah, we also kindly invite the interested audience to participate. And okay, so I think due to the limited time, I think that's all for today's talk. And if you have more questions, you can feel free to ask me or Dr. Amit Sharma. I think, and I also I think this will motivate a lot of brilliant research articles. So motivated by Dr. Amit's great talk. So yeah, since there's no more questions from the audience, I want to thank you for the time and efforts. You know, for from the Dr. Amit Sharma. So for delivering such a brilliant talk about the causal reasoning and large language model. So thank you so much, and Dr. Amit, and maybe that's the end for today.
Great. Thanks for inviting.
Yeah, thank you so much. Yeah, really great work and influential work. Yeah, we will help you to announce, in the Chinese community to let more people to read this work and have a deeper insight. So thank you so much.
Yes. Thank you. Bye-bye.
Yeah, bye-bye.